We're going to look at how we prepare alcohols from other organic compounds, and this is going to be a bit of revision because the reactions we're going to look at we've already covered in previous topics. So in the first year we look at only two ways of making alcohols, and they've been covered before in previous topics. In the second year we look at other ways of making alcohols from aldehydes, ketones and esters, etc. We'll learn a bit about aldehydes and ketones later on when we look at the reactions of alcohols. But for now, to prepare alcohols, we just look at two of these reactions, one from alkenes and one from halaalkanes. You may remember when we did alkenes and we looked at the addition reactions of alkenes, one of the addition reactions was the hydration of alkenes. So here we got an alkene here and we got steam, and for hydration we need phosphoric acid as a catalyst and 300 degrees C as the conditions. We also write 60 atmospheres as the full conditions for this reaction. Now you also may remember that with an asymmetrical alkene like propene and an asymmetrical reactant like steam, which can be drawn like that, which shows it's asymmetrical, you can get two different products because you can have the partial positive, the hydrogen, attracting the electrons from the pi bond in the alkene, and they move towards the hydrogen there. And as those electrons approach the hydrogen, the electrons in this bond will be repelled away from these electrons, so these will repel towards the oxygen, and the oxygen accepts those electrons to form a stable hydroxyl ion. You may remember that you will get either the hydrogen bonded to this carbon here, that means the carbon here is now electron deficient and we get this carbocation, this primary carbocation, or you get a situation where you get the hydrogen bonded to carbon there and you're left with the carbon here being electron deficient because that pair of electrons no longer share between the carbon here, and therefore the positive charge will be on this carbon and we get a secondary carbocation. So therefore we have two possible scenarios, and then we could have either the electrons from the hydroxyl ion attacking that secondary carbocation, or in this case the primary carbocation, and we get two different products at the end. So we can either have propan-2 or the propan-1 being formed. So these are the alcohols that we prepare from the alkenes through hydration. And you may remember from Markovnikov's rule that the major product out of these two will be the secondary alcohol, as it is formed from the more stable secondary carbocation intermediate. So here's maybe one way of remembering all the conditions for hydration of alkenes. So imagine in a few decades' time, global warming has heated up the earth so high that it's 300 degrees outside, and every hour of the day you're going to feel that pressure of 60 atmosphere pressure, and so that heat's going to cause you to steam and produce lots of steam. So you feel really hot and you're going to grab a nice cold drink. So you're going to grab a can of Coke which contains phosphoric acid. So you can hydrate yourself using some phosphoric acid solution, basically. So alkenes can be hydrated using phosphoric acid catalysts and steam and 300 degrees C and 60 atmosphere pressure. Under pressure. So the second way to produce an alcohol is from hydrolysis of haloalkanes. So again, this is a reaction we've already done when we did haloalkanes. You can hydrolyze haloalkane using water, but as you remember, that's a very slow reaction. So what we do in practice, we use an aqueous alkaline solution like sodium hydroxide to provide hydroxyl ions which will attack the partial positive carbon on this dipole here, and that acts as a better nucleophile. So the reaction with an alkaline or aqueous alkaline is faster than with water. So the partial positive carbon here is attacked by the electron pair on the hydroxyl ion. So we get the arrow from the electrons to that partial positive, and as those electrons approach, the bonding pair electrons here can repel towards that bromine, and we get the alcohol that's formed here. And we also get substituted out the bromine ion here. So this is a substitution reaction, and this mechanism is nucleophilic substitution. You also may remember that different haloalkanes undergo hydrolysis at different rates of reaction because of the difference in activation energy due to the difference in bond enthalpies between the carbon and the halogens. So that's a bit of revision as well. So this covers all the reactions, the two reactions that we need to know for the first year in how to prepare alcohols. There are other reactions that involve aldehydes and ketones in the second year, which we can use to prepare alcohols. but we'll look at those later.